Hello and welcome to this lecture. Now that we've seen various small cases, two variables, two equations, two variables, three equations, three variables, two equations, three variables, three equations, we're ready to jump into the more general scenario of m linear equations in n variables. So we'll see the principles we use will exactly be the same. It will be elimination followed by back substitution. But nevertheless, there are some small things to pay attention to, maybe the form of the solution, etc., etc. So what I'll do is I'll do a whole bunch of examples to show you what are the different things that can happen when you have larger number of equations and variables, and then go back to our old problem of the web search problem and the polynomial fit problem and actually solve those, and then conclude with a general remark on how these things look. Okay, so that will conclude the study of systems of linear equations. Okay, so let's begin with 5 equations, 5 variables. Why 5 and 5? Easy enough number for me to use. You could use something larger as well. So instead of showing you the equations and the variables and all the gory details, I'm just showing you the matrix. So you see how easy it is to succinctly sort of represent the problem. You can add the variables on top, right? You can add the variables here. Maybe you should have this. So you can add the variables on top if you want, x1, x2, x3, x4, x5. Okay, I have not done that. I'm not showing you that. These are equations, so you know how to read these equations, right? The first one is 2x1 plus 2x5 equals 1. So this dotted line represents that this is on the right hand side. This is the 5 by 5 coefficient matrix on the left hand side, right? So this is the way the equation works. Now if you look at this matrix, how do I start the elimination process? I start with the pivots. No, I first start with 1, 1 location. I see that the pivot here is non-zero, right? So if it were 0, I might have to do some swapping, but this is already non-zero, so there's no swapping required. So everything below the pivot, I have to make 0, right? So that is the process of elimination. Everything below the pivot should go to 0. So how do I do that here? I have to do R3, the row 3 is replaced with row 3 minus row 1, right? That's the first step I do here. And then similarly, R4, the fourth row is replaced with R4 minus R1. Okay, so I replace these two equations with the variance of them. Now I get another equivalent system of linear equation, except that there is the pivot which is non-zero, and below the pivot everything is 0. Okay, so I'm going from a generic square form for the matrix to an upper triangular form, right? So that's the idea in the elimination process. So I finished 1, 1. Then I go to the next stage, which is 2, 2 location. In the 2, 2 location, I already see I have a non-zero pivot. So once you have a non-zero pivot, no swapping is needed. Below that, everything has to become 0. So I have to make the fourth row 0 here, right? So what do I do for that? I do R4 is R4 minus 2R2, right? So R4 is R4 minus 2R2. So once the first row is done, I'm not going to deal with that again. Remember that. Okay, so it's like I'm having a smaller problem here. I'll only deal with this part of the matrix, right? So you do R4 is R4 minus 2R2. Everything to the left of it is 0 anyway, right? So whatever you do here, nothing will change. It will just be 0, right? So you see here I've done 2 minus 2, 0, 0 minus 2 has become minus 2 here. And then this is 0 again. And then this is minus 1 again. 1 minus 2 has become minus 1 here. So this is what I've done here to the fourth row. I've done this operation R4 minus 2R2, and that became 0. So now this pivot is done. I have to now jump to this pivot. But here I see that in the 3, 3 location, my pivot is 0. So I need to make it non-zero. And there are two options here. I can either bring up the fourth row to the third row or the fifth row to the third row. Okay, the row swap is possible. So row swap is the first thing you have to do, right? So you can do that here, but then this is a choice, and depending on what you choose, your form for the upper triangular matrix will change. Okay, so what have I chosen? I've chosen to exchange R3 and R5 just for convenience. You can also do R3 and R4. It's just a choice. You can do whatever you want. So I've done that. So I've just swapped these two rows. I've got 2, 1, 1, 0 going in the third row and now coming below. So now I have a non-zero pivot here. I can make everything below it 0. Right, so this is non-zero. I have to make that 0. So if I do that, I have the form here. So I'm done with 2. Below this is it's all 0. Then I go to the next pivot. Guess what? Below that it's all 0. Next I go to the next one. It's again a non-zero value. So my elimination process is done. Okay, wonderful, isn't it? So, so you can just do step by step. If it's not done, keep proceeding till it is done. Okay, so this was my first example, and the elimination process is done. Once the elimination process is done, you have to start the back substitution. Okay, so the back substitution here, you start with the last non-zero equation. Okay, and you see there that that non-zero equation is a very simple one. It's minus 2x5 equals minus 1, and that is just one variable one equation. Okay, the goal is to go to one variable one equation. You do that, you can solve that, right? So x5 is 1 by 2. Now once you have this this one solved, you go to the previous non-zero solution here. Because of this upper triangular structure, once you solve this guy, you can solve the next one. Okay, so the next one is what? Next one doesn't involve x5 at all. It's just x4 equals minus 1. Very, very simple equation. Then you go to the next one, the third one here, and that is 2x3 plus x4 plus x5 equals 0. So you use x4 equals minus 1, and you use x5 equals half, and then substitute here. Minus 1 plus half is minus half. It goes to the other side, becomes plus half. This 2 divides, it becomes 1 by 4. Okay, so x3 is 1 by 4. Then I go to the next equation. Okay, that is this guy. It says x2 plus x3 equals 1. Okay, and then I use x3 from here. You see that x3 is 1 by 4, x2 is 1 minus 1 by 4, that's 3 by 4. Then finally I go to the first equation, and that is just 2x1 plus 2x5 equals 1. You use x5 equals half from here, this cancels, and you get x1 equals 0. So there you go, that's the answer. x1 to x5 I have solved, and I've got a unique solution. The moment you see that this entire thing has gone down all the way, the back substitute, the elimination process went all the way to the final thing, and you got a square upper triangular matrix with non-zero pivots. You know that this is going to be unique solution in this fashion. Because every equation has one solution, and you got a unique solution. So you got a unique solution here. So the first example I took, more general example, 5 equation, 5 variables, ended up being a unique solution situation. So you may get this. You may get this in any situation, and you can solve for it in this fashion. So this is just one example to show you what may happen. Here's another example: 5 equations, 3 variables. Okay, so I've taken a slightly different situation, a simple looking example here. Once again, you can see this is compressed notation. It's just the matrix here. I have not shown the x1, x2, x3. I have not shown all the equations. Just this right hand side values are here, left hand side coefficients are here. It is 5 equations, 3 variables, right? So you see the power of this simple notation. It gives you ways of doing it. Okay, so once again, let's start the elimination process, right? So you have a non-zero pivot here, 2, and then below that I have to make everything 0. Okay, so notice what I'm doing here. R2 is R2 minus R1, R3 is R3 minus 0.5 R1, R5 is R5 minus 0.5 R1. Okay, 3 equations, 3 operations. These are called row operations, by the way, in case I didn't mention it earlier. These kind of operations in elimination involving combination of rows is called row operation. Okay, so that is some word you will see quite often if you look at elimination process. So below this pivot, I'm able to make everything 0. I have done that here. You can check that I've done this correctly. I hope I've done this correctly. So below 2, I have everything being 0. Okay. Once I'm done with this, I have to come here, and guess what? This pivot is this value is 0. Okay. Now I have to do a row exchange. Pick one of your favorite rows, 3 or 4 or 5, and exchange it to the first one. I don't know what I've done here. I've exchanged R2 and R3. Okay. These two have swapped. So this one has come on top. This one has come below. And then now I have a non-zero pivot here in the 1, 1 location. And then below that, I have to make things 0. Right. So that's my operation. So I have 2 more row operations left here. R4 is R4 minus R2, R5 is R5 plus R2. Once I do that, below this pivot, I have 0 values. And then I have the next pivot here, minus 1. And below that, there are some non-zero values. Okay, so at this point, just mechanically do the elimination. Don't think about what it means in terms of equation or not. Just mechanically do the elimination. So below this, I'm going to make these guys 0. And that is just R4 is R4 plus 0.5 R3, R5 is R5 plus R3. So below this pivot also, I've made it 0. But guess what has happened here? Right? I'm below this pivot, I made this 0. But then I have a 0 equals a non-zero situation. Both equation 4 and 5 are inconsistent. So anytime you have an inconsistent situation like this, your system is not going to have a solution. There is no solution, no value of x1, x2, x3 can satisfy all these 5 equations. So notice how this elimination, right? It changed the system of equations, always keeping it equivalent. All of these systems of equations that we get through the elimination process, they're all the same. They represent the same system. And finally, it comes to a form where it's apparent that there can be no solution to this. 0 equals 2.5 is not going to happen wherever you go in this world or any other world, right? So it's not going to happen. So that's inconsistent equation. So from an equation which looks, this equation, it's not obvious that it's inconsistent, no. So, but this elimination process clearly tells you that those are actually inconsistent, because we got a very obvious wrong equation, which was actually hidden in those equations also. Okay, so that's the moral of the story here. So 5 equations, 3 variables, you can get no solution. It turns out you can also get infinitely many solutions. You can get unique solution, no solution, infinitely many solution. We saw that in every case. So in the general case also, it should be possible. But to show you examples of infinitely many solution, it turns out we can go back to our original examples. What were our original examples? There were 2 examples that we are yet to solve from the original ones. The circuit one we already solved. The second one was the web search example. You remember this one? We had these web pages with importance values assigned to them, and there were these 5 equations that we obtained from them. These 5 equations, I can convert them into this matrix form. I'm just showing you literally here. So this is how it happens. x0 minus x3 by 3 is 0, and you get this. So here is a system which has got all zeros on the right hand side. There is no non-zero coefficient on the right hand side. Everything is 0 on the right hand side. Such a system is called a homogeneous system of equations. When you have only variables being equal to 0, equal to 0, equal to 0, like that, if you have every equation has no constant term, right? Only x terms, x1 term, x2 term, like that, those equations are called homogeneous equations, because there is the degree of every term is 1, right? So there's a homogeneity in the degree. So that's why degree is basically something to do with the power of the variable in every term. The power of variable in every term is 1, right? So that's degree 1 in every term. That's homogeneous equation. Okay. So homogeneous equation also is solved the same way. It doesn't matter, except one thing to keep in mind is when you have a column of zeros, any operation you do, any row operation you do, this column of 0 is not going to be affected. So this column of 0 is like a useless column you're carrying along. You can as well drop it. If you're comfortable with that, you can drop it. But anyway, we'll keep it. It's okay. It doesn't hurt us too much. Just drawing a whole bunch of zeros. Okay. And then you can manipulate here. Okay. So again, the principle is the same elimination process. You start with 1, 1. It's non-zero here. I make everything below that 0. So I do R2 is R2 minus R1. And then I come here, this is non-zero, I have to make everything below that 0. So I do R3 is R3 plus half R2, R4 is R4 plus half R2. Then I've done that also. Then I come here, I see I have a non-zero pivot, and then I have to make all these things below 0. I do those operations, and then I end up with. So now I have this equation here, minus half, 1, half, minus 1, 0, 0. What do I do now? I can again do, below, I have a non-zero pivot here, below that I have to make it 0. So R5 is R5 plus R4, I get minus 1 by 2, 0 here. So notice what has happened here. For the first time we are seeing this in these examples. I got an all 0 row, right? Left hand side is 0, right hand side is also 0. So this is not an inconsistent situation. It's not like I got 0 equal to 2 or 0 equal to 1 or something. I didn't get that. So it is still consistent, except that the last equation is gone, right? So all 0 rows, you can throw them away. They're not going to, that's not an equation at all. 0 equals 0. It is an equation, but it's always satisfied, right? 0 equals 0. So you don't have to bother about it. So this you can throw out, okay? So now you have to start your back substitution, okay? So how do I start my back substitution here? See, the first equation I have here already involves 2 variables, right? It doesn't just involve 1 variable. So when I see a situation like this, what should I do? I should do the parameterization, right? And I can expect infinitely many solutions here. So the one of these variables, in fact, usually it is customary to pick the last variable here. So x5, I will pick x5 and make a parameter out of it. Okay. So then what will happen? Let's do that. Okay. So let me just write down the last equation that I have here. The last equation I have here is minus x4 by 2 plus x5 equals 0. So I'm going to set x5 as this u, my parameterization, right? So I'm going to write, it's like a free variable. The way of putting it, I can pick any x5 I like and treat this u as part of the right hand side in this equation and solve for it, right? So once I do this, I'm going to get x4 equals 2u, right? I move it to this side, multiply the 2, I get x4 equals 2u. So that is how I solve this equation. So I put x5 equals u, then I put x4 equals 2u. And then after that, what do? Go to the next equation. So again, back substitution goes in the same way. I mean, you do the same back substitution, except that all these free variables, you assign some parameters and solve the other variables in terms of the free variables. That is the idea. So you got one free variable here, which was this x5. I made it u. Once I made it u, after that, the back substitution will work exactly like before. There's no problem here, right? Because I've got that upper triangular form. I can find x4. Then using x4, I can find x3. I can go on and on like that. That's what I'm going to do. This u that I have here is going to be hanging around, but that's okay. All my answers are going to be in terms of u. Okay, so that's the idea here. So let's go to the next one. The next equation is minus x3 plus, just make sure I get that right, minus x3 plus x4 by 3 equals 0, right? I'm going to put x4 equals 2u here, bring this to the other side, I get x3 equals 2 by 3u. Okay, so that's another solution for you. Now that I know x4 and x3, I move on to the next equation, and that equation is also very simple. It says minus x2 plus x4 by 2x4 by 3 equals 0. So this tells you x2 is going to be 2 by 3 times x4, which is 4 by 3u, right? And the last equation is x1 minus x4 by 3 equals 0, and that tells you x1 is 2 by 3. Okay. Did I get that right? Okay, I hope I got that right. Let me see. Oh, okay. I'm sorry. So the one thing I messed up is, sorry, apologies for that. It's x0 to x4, not x1 to x5. So let me just go there and make that change. Make all these things one lesser. I was wondering why I made some silly mistake here. The variables are not x1 to x4. So it is x3 plus x4. x4 is u, x3 is 2u, x2 plus x3 by 3. So x2 becomes 2u by 3, and then x1 plus x2, sorry, x3, and x0, x3, so x1 is 0. Okay, so apologies for this mistake in the terminology here. So, but that's okay. It's not too bad. So I get my final solution, all of them in terms of u. So that's what I've written down here. So you see x4 is u, and then x3 became x4 is u, and then x3 became 2u, x2 became 2u by 3, x1 is 4u by 3, x0 is 2u by 3, so on. Okay, so that's the solution here. So notice here we got a situation where there are infinitely many solutions. For every u, this is a valid solution for this system of linear equations. And that happened because it turned out one of those equations is 0, and you ran out of pivots. I mean, you got only 4 pivots for 5 variables. So one of the variables became free, and that variable you can assign any value you like, and you will still get a solution. Okay, so you get a larger, big, much, infinitely many solutions. And this is our favorite way of writing this down, right? So we'll write the solution as x0, x1, x2, x3, x4 in this vector form. This vector 2 by 3, 4 by 3, 2 by 3, 2, 1 multiplied by u for every u. So now remember what we wanted to do with this web search. We wanted to find out which is the largest, which node or which page has the largest importance. So here if you see all these coefficients, of course there is u there, and maybe you can take u to be equal to 1 or normalize it in some way. So you see that if you take u to be 1 like that, this guy is the maximum, right? So this guy is the maximum. So in your web page, which you have to display, right? The search results you have to display. you will display that page first. Okay, next you go to the next most important one, maybe the first page, right? X1, which is 4 by 3, and then you go to 1, and then you go to the 2 by 3, guys. So this is the ordering in which you display the web search results, and this has worked out very well for Google, hasn't it? So it's a nice method to follow. Okay, so that's the web search example. This is the first example we are seeing where we got infinitely many solutions, and we had to parameterize to write it down. Okay. So the last example I want to show you is the polynomial fit example, which we saw earlier. You remember the equations? It was this picture of the polynomials. We had to pass through 1, 0.5, 2, 2, and 3, 1.5. Those are the 3 points I've shown here in blue, right? And then I need a degree 4 polynomial, which is going to actually go through these points and all possible polynomials of that type, right? So if you write down the equation, you see that you get the first equation is just a plus b plus c plus d plus e is 0.5, putting x equals 1, right, in that polynomial. Second equation is 2 power 4. I mean, instead of x equal to 2, I'll have to substitute. So ax power 4, it becomes 2 power 4, etc., etc. So you have this equation. You can write down the system now. The variables are a, b, c, d, e. 1, 1, 1, 1, 1, 0.5, 16, 8, 4, 2, 1, 2. 81, 27, 9, 3, 1, 1.5, right? 3 power 4 is 81, 3 power 3 is 27, so on. Okay. So you got 3 equations, 5 variables. Now, I'm going to do a little bit of a permutation here, column swapping, to make my work easier. I mean, I don't want to deal with these big bulky numbers like 16, 81. I can deal with 1, 1, 2, 3, you know. That's good enough for me. So I'm going to swap this so that E comes first. Okay, and this is okay. You can do column swap. I have not told you what swap I've done here. A and E have exchanged, D and B have exchanged. Okay, this is okay. You should remember that you did the column swap. Don't forget that you did the swap. So it's good to write down the variables on top whenever you do a column swap. After this, it's exact same elimination as before. I've got a non-zero pivot here. In fact, this column swap is not necessary. If you think you can handle 16 and 81, go ahead. You can go ahead and eliminate the pivot 1 here, and below the pivot you can go ahead and eliminate. That's perfectly fine, nothing wrong. I'm just doing it to show you that these things are possible. Okay, in fact, numerical algorithms, when they have large matrices, have to pick their column sort and all carefully, column order and all carefully, because only then it will be stable and all that. So it's an important part of the numerical evaluation. So how do I make everything below 1, 0? I'll do the row subtractions. That's what I've done here. So I've got that. I've got this system now. This is, once again, you remember every system that I obtain after row operation, column swapping, row swapping is completely equivalent to the original system of equation. Okay, so that's the power of the elimination process. Okay, and then I have a second pivot here. I'm making everything below that pivot 0 with row operation, and then I'm done. Right. So I've got my row operations are finished. My elimination process is over. And I've run out of pivots, right? I've got only 3 pivots, but there are 5 variables. So there are 2 more variables left, and those I can pick any which way I want, right? So what I'm going to do, there are 2 parameters. B is a parameter, and then A is a parameter. So this B parameter I'm picking as U, A parameter I'm picking as V. Now, in fact, you don't have to do this. B is U, A is V. I'm just doing it for convenience. You can simply keep this as B, keep that as A. If you're comfortable with that, you can work with that also. It's not wrong. But anyway, I've done this. We've been doing it always. So once you do this, you get this last equation, right? After this, back substitution starts. Once you figure out the parameters in your free variables, back substitution starts as usual, and your free variables are treated as constants, right? So you move these guys to the right and solve for the dependent variables, EDC. By the way, these two A, B are free variables. The other variables are called dependent variables, right? So you solve for the dependent variables using these equations in terms of the free variables. That's what you do in the back substitution process. Okay, so you do that. It's quite easy. You can write this equation out and then solve it. I'm going to cut this work short a little bit. You can solve this equation and get this one. C is minus 1 minus 6u minus 25v. It's very easy to do that. And then use this back in the second equation and solve for D. You will get D is 4.5 plus 11u plus 60v. Okay, I'll let you play around with that. Check it out. It's an easy calculation. And then I use the first equation and use all these values C, D, A, B, all of them, and I'll get E equals minus 3 minus 6u minus 36v. And now again we have an infinitely many solutions. not just one-dimensional infinity, there are two-dimensional infinity, right? So u can be any value, v can be any other real value. So there are two free dimensions I can pick. So this is supposed to be like a two-dimensional solution that is possible for these 5 variables passing through satisfying these 3 equations. Now we also have our favorite form for writing this equation out, right? This a, b, c, d, e can now be written in vector form, a constant vector plus a vector multiplying u plus a vector multiplying v. Okay, so once again you can check that this is correct here. So for a is just b, right? There is no multiplication of u, there is no constant, only v, so it just becomes 1. B is just u, so there is no constant, constant vector is 0, the vector the coefficient multiplying v is 0, the coefficient multiplying u is 1. On the other hand, if you look at C, there is a constant value -1 that shows up here. There is a value that multiplies u -6 that shows up here. And there is a value that multiplies v -25 that shows up here. So you see C is -1, -6u, -25v. We're rewriting the same thing here. It's nothing different except that it's written in vector form. Likewise for D, likewise for E. Okay, constant term shows up here. The term multiplying, the coefficient multiplying u shows up here. The number multiplying v shows up here. And this is the vector form of the solution for these variables a, b, c, d, e. For all u and all v, these are solutions. So u is any real number, v is any real number. So that's what I meant by saying it's a two-dimensional solution. These are called planes in 5-dimensional space. Okay, how to visualize that? You visualize it. So it's not just a plane. It's not a plane through the origin. It's a plane that's translated away from the origin. It's almost like a straight line, but it doesn't go through the origin. It's a little bit away, right? The translation is this vector, and these two are the angles at which the planes work. Okay, so that's the form of the solution. For every u and v, I get a value of a, b, c, d, e, which is a valid solution to this equation. What does that mean? It means that for every value of u and v, the coefficients you get, a, b, c, d, e, defines a 4th order polynomial, right? So I'm working with the 4th order polynomial, no? Ax power 4 plus bx cubed plus cx squared plus dx plus e. That 4th order polynomial passes through the points 1, 0.5, 2, 2, 3, 1.5. Okay, you might wonder, is this really true? Because that's how we started the problem, no? The polynomial fit. Let's go to Desmos and verify that this is true, right? So let me go to Desmos. So you can see what I've done here in Desmos. I have my 3 points, 1, 0.5, 2, 2, and 3, 1.5. And then I put my 2 parameters a, b, and what I've done here is I've written the polynomial equation ax power 4 plus bx cubed plus c. C is what? C you can see is 1 minus 6u minus 25v, right? U was b and then v was also a. So I've written that here. That is c. And then I've written d here. D is 4.5 plus 11b plus 60a. And then I've written e here. E is minus 3 minus 6b minus 36a. Okay. And then I put sliders here for a and b. Right? A and b are my free variables. A and b can be any real number I want. And for every real number, I get a polynomial that has to pass through these 3 points. Okay, notice here, I vary b. When I vary b, notice what happens. This polynomial is sort of, slithering around, moving around like some sort of a rope, but it's hanging on those 3 points. It cannot go anywhere else. And whatever value of b I pick, so notice, ooh, it's gone all the way here. After this, maybe not changing too dramatically, but notice some dramatic changes that happen here. It goes off all over the place. Maybe we can zoom out a bit if you want to see some more way in which it operates. So you notice it's moving away a lot, and then as I move around, it's moving away this direction. If I in fact change this value more, it will move a little bit further. But anyway, okay, so let's see that. So that's b for you. And then I can vary a also. Notice if I vary a, more interesting things also happen. Okay, so you see that around 0, there is a dramatic shift in which the way the polynomial behaves. We'll see some of these things later on. Okay, so you see, but notice whatever I do to a and b, the polynomial always passes through my 3 points that I have picked here, right? So I can't, whatever I do, I can't do anything to that, right? Interesting, isn't it? So our solution is not, it's definitely not wrong. For every possible value of A, B, C, D, E that I picked here, the curve, the polynomial curve is indeed passing through the 3 points I wanted it to pass. Okay, so we've done the polynomial fit carefully. Okay, so let me summarize what's going to happen in general when you have m equations, n variables. Okay, so this is the form of the equation. Notice once again how the notation, this aij notation, the xi notation, the bi notation, right? x1 to xn, b1 to bm, and then a11 all the way to amn neatly extends. There's no need to put any additional variables or something. It just very cleanly extends, and the matrix form is also very nice to write down in general. So we can do that, and then you start the elimination and back substitution process. Okay, so that's how you solve the elimination back substitution. So elimination can involve row column swaps and row operations. And we saw the way in which we do the row operation. No, you always replace a row by that row minus some constant into pivot. Okay, be careful about that. Don't do some other arbitrary operations of rows. Even if you know what you're doing, you can do it, but there's something involved there. Be slightly careful. Always do only this R, row equals row minus constant into pivot row. That will not be wrong. You'll be perfectly fine. Okay, so I've drawn a picture here to illustrate the upper triangular structure, the generic form of the upper triangular structure you may get at the end of the elimination process. Hopefully it's clear. It's a bit of a complicated looking diagram. I was thinking about whether you can make it any better. Maybe you can make it better. If you have a better picture, please feel free to send me. So you will have an R by R part, a square part here, which corresponds to all your non-zero pivots that you got. Okay. Now what is going to be this value of R? It depends on the actual problem, right? We saw just before in this example, what is the value of R? R is 3, right? See, notice there are only 3 pivots that I found. So R is the number of non-zero pivots that I find, and that corresponds to the square part of the matrix. Here it was 3. If you go to the web search example, you just go to the web search example. In the web search example, you see R was 4. I found 4 non-zero pivots, and I got the square form for the the square matrix, the upper triangular matrix here with all non-zero diagonals. R was 4 here. And then there may be situations where R is 5 also, right? Let me just go quickly to, so here is again a situation where I got R equals 3, right? Here again R was 3, I found 3 non-zero pivots. And then there was this original case where we had 5 equations, 5 variables. I found 5 non-zero pivots. Okay, R was 5. So this value R, let me see if I can quickly go here. This value R that I have here can actually be any number. It can even be 0, right? If the entire matrix is 0, it's 0. It can be 1, it can be 2, it can be 3, it can be 4, it can be 5, it can be 4. It can go all the way up to n. Okay, R can be 0, 1, 2, 3, 4, 5, all the way up to n. How many pivots I can find? I can find up to n pivots. And now you should also keep in mind, you may run out of rows or columns. Okay, so it's not always n. It's in some sense the minimum of m and n. Okay, so you may run out of rows before you run out of columns. Okay, so that is something to keep in mind. Okay, so this R is some number that will you'll get. It depends on the number of pivots, non-zero pivots that you can possibly get. You may run out of pivots for various reasons. You may run out of rows, you may run out of columns, you may run out of zero values in the matrix, right? All of this can happen, but R is the number of non-zero pivots I get in the elimination process. For this square matrix, the square coefficient matrix on the left, the m by n matrix, this number R is also called the rank of the matrix. Okay, so if when you study matrices and linear algebra, this will come in. This is the rank of the matrix. It's a very important number. It has a lot of interesting properties. Okay, so anyway, so this is the pivots that you get in this thing. Now, what are the properties we know once you run out of these pivots? Everything below the pivot in the square part will be 0. And everything below those pivots on the left hand side, right, will be 0. Right? They have to be 0, because if it is non-zero, I can go find a pivot, isn't it? So all of these guys will be 0. Okay. And what about these parts here? These could be non-zero. Okay. So this upper triangular part here can be non-zero. The square part here can be non-zero. This part here on the right hand side can be non-zero. This part here could be 0 or non-zero. Okay. Depending on how this b tilde r plus 1 colon m, what is this notation here? B tilde r plus 1 colon m. So this is sort of like a programming notation. It says this part of the right hand side coefficient from r plus 1 to m, right, from r plus 1, wherever my pivot ended, r plus 1 to m, that vector is denoted as this b tilde r plus 1 colon m. Why am I saying b tilde and not b? Shouldn't it just be b? Why am I saying b tilde? Think about that for a couple of minutes. Any particular reason why you put a b tilde here? Why am I not saying b? Why is it not the same as b? Because of these row operations. Because when I do row operations, all these values change. The coefficient values also change. So this will be some modified value. It will not be the same thing here. It will be some modified. So this is the vector which is below the pivot, right hand side coefficients below the pivot. Okay. Now this is the general form of what you will get after elimination. You have to sort of identify all these forms. Once you've done with the elimination, you have to identify R, you have to identify this part. Okay. This R and this part play a role in the nature of the solution. Okay, so what will happen here? There are various possibilities. One possibility is R ended up being less than n. So one thing that can happen is this number of pivots you found can be less than m, that the number of equations you originally started with, and these right hand side coefficients are not 0. So here you have an inconsistent case, right? So we already saw this once before when we had 5 equations, 3 variables, it ended up being inconsistent. So if this ends up happening, then you have no solution. So this is first case. Okay, this is the way in which one can happen. Now there's also another case. Okay, so that is the first case. Okay, when you have this all zero part violating, I mean something here ends up being this part is there, and it ends up being non-zero, and then that will give you no solution. So that's clearly an easy case to deal with. The next case is when this br plus 1, this part is either 0 or it's empty. Basically, so whenever we have this all zero part here, this also is 0. You in fact you throw those equations out and make them empty. So when that part is empty, okay, there can be two different solutions. Okay, what are the two different possibilities? First one is this r could be equal to n. Okay, this r could have come all the way till the end, and then there is nothing else left. Okay, then you will have a unique solution. So you go back to the first example I dealt with here. It was 5 by 5, right? You ended up having 5 pivots, and then when you back substitute, you'll get only one solution everywhere. Okay, so that's the unique solution. You can also have this part being empty. There is no inconsistency. There's no issue with consistency, but r became less than n. The number of pivots you found is less than the number of variables that you have. In that case, you will have n minus r free variables, and you will have an n minus r dimensional solution for your problem. You'll have infinitely many solutions, and there will be n minus r free variables. You'll have to parameterize them and then move them to the right and solve for the pivot variables or the dependent variables in terms of the free variables, and you will get that solution in that many dimensions. There will be n minus r dimensional solution for this problem. Okay, so this one slide conveniently captures all that we do in solving systems of linear equations. Hopefully you understand it. Spend some time with it. Hopefully I have not made any mistakes in these conditions. I think they are correct. So you may have an inconsistent thing. If you don't have an inconsistent thing, then everything depends on how your number of pivots or rank compares with the number of columns n. Okay, so that's the conclusion of this lecture. I hope this linear systems of equations is comfortable for you now. It's an important field of study, and you have to be able to understand how to solve systems of linear equations, and more importantly, you have to understand how the solution will look. The fact that the solution is either a unique vector, or there is no solution, or there is a linear combination of multiple vectors, a multiple dimensional solution, is very important to take forward into your future studies of mathematics or applications in science. Okay, thank you very much.